Exhaust manifold. 1. Collects exhaust gases. The exhaust manifold gathers exhaust gases from each engine cylinder and channels them into a single exhaust pipe. 2. Bolted directly to the engine, it is mounted to the cylinder head, making it one of the first components in the exhaust system. 3. Made from heat-resistant materials, commonly built from cast iron or stainless steel to withstand extremely high temperatures. 4. Handles extreme heat. Exhaust gases passing through it can exceed 800 to 900 degrees Celsius, 1470 to 1650 degrees Fahrenheit, during normal operation. 5. Affects engine performance. A well-designed manifold improves exhaust flow, helping the engine breathe better and produce more power. 6. Cracks are a common failure. Constant heating and cooling cycles can cause cracks, leading to exhaust leaks and loud ticking noises. 7. Works with a gasket. A manifold gasket seals the connection between the manifold and cylinder head to prevent exhaust leaks. 8. Can impact fuel efficiency. Exhaust leaks before the oxygen sensor can cause incorrect air-fuel readings, reducing fuel economy. 9. Connected to emissions control, it directs gases toward the catalytic converter, playing a role in reducing harmful emissions. 10. Performance versions exist. Aftermarket headers are performance-style exhaust manifolds designed to reduce back pressure and increase horsepower. Oxygen sensors, O2 sensors. 1. Measure oxygen in exhaust gases. Oxygen sensors detect how much oxygen remains in the exhaust after combustion. 2. Help control air-fuel mixture. They send data to the engine control unit, ECU, so the engine can maintain the correct air-fuel ratio. 3. Improve fuel efficiency. Accurate sensor readings help the engine burn fuel efficiently, saving fuel and reducing waste. 4. Reduce harmful emissions. Proper oxygen sensor operation helps lower emissions like carbon monoxide, CO, and hydrocarbons, HC. 5. Located in the exhaust system, they are typically installed in the exhaust manifold and after the catalytic converter. 6. Most cars have multiple sensors. Modern vehicles usually have at least two. One upstream, before the catalytic converter, and one downstream, after it. 7. Operate at high temperatures. Oxygen sensors need to be hot, around 300 to 600 degrees Celsius, to function correctly. Many have built-in heaters. 8. Wear out over time. Oxygen sensors commonly fail between 100,000 to 160,000 kilometers. 60,000 to 100,000 miles. 9. Faulty sensors trigger warning lights. A bad oxygen sensor often causes the check engine light to turn on. 10. Affects engine performance. Failed sensors can lead to rough idling, poor acceleration, increased fuel consumption, and failed emissions tests. Catalytic converter. 1. Reduces harmful emissions. The catalytic converter converts toxic gases like carbon monoxide, CO, hydrocarbons, HC, and nitrogen oxides, NOx, into less harmful substances. 2. Part of the exhaust system, it is installed between the exhaust manifold and the muffler. 3. Uses precious metals. Inside it contains catalysts such as platinum, palladium, and rhodium that trigger chemical reactions. 4. Works at high temperatures. It operates most efficiently when hot, usually above 400 degrees Celsius, 750 degrees Fahrenheit. 5. Converts gases chemically. Colorado becomes carbon dioxide, hydrocarbons become water and carbon dioxide, and NOx becomes nitrogen and oxygen. 6. Essential for emissions laws. Modern vehicles cannot meet emissions regulations without a functioning catalytic converter. 7. Can get clogged or damaged. Engine misfires, oil burning, or coolant leaks can overheat and destroy the converter. 8. Affects engine performance. A blocked converter can cause loss of power, poor acceleration, and engine overheating. 9. Has upstream and downstream sensors, oxygen sensors before and after it monitor efficiency and emissions performance. 10. Target for theft. Due to valuable metals inside, catalytic converters are commonly stolen from vehicles. EGR, exhaust gas recirculation, valve. 1. Reduces nitrogen oxide, NOx, emissions. The EGR valve lowers combustion temperatures, which helps reduce harmful NOx gases. 2. Recirculates exhaust gases. It routes a small amount of exhaust gas back into the engine's intake system. 3. Improves emissions compliance. The EGR system helps vehicles meet strict emissions regulations. 4. Operates mainly at cruising speeds. The valve is usually active during steady driving, not at idle or full throttle. 5. Controlled mechanically or electronically. Older vehicles use vacuum-operated EGR valves, while modern cars use electronically controlled ones. 6. Prevents engine knocking. By lowering combustion temperatures, the EGR valve reduces the chance of detonation, knock. 7. Can clog with carbon buildup. Soot and carbon deposits are common causes of EGR valve failure. 8. Faulty EGR affects drivability. A bad EGR valve can cause rough idle, stalling, hesitation, or poor acceleration. 9. Triggers warning lights when faulty. EGR problems often activate the check engine light with emissions-related fault codes. 10. Requires periodic maintenance. Cleaning the EGR valve and passages can restore proper operation and extend engine life. PCV. Positive crankcase ventilation valve. 1. Controls crankcase pressure. The PCV valve regulates pressure inside the engine crankcase by venting blow-by gases. 2. Reduces harmful emissions. It routes unburned fuel vapors and gases back into the intake manifold to be burned again. 3. Improves engine efficiency. Reburning blow-by gases helps improve fuel economy and engine performance. 4. Prevents oil leaks. Proper crankcase ventilation reduces pressure that could otherwise force oil past seals and gaskets. 5. Usually small but critical. Despite its small size, the PCV valve plays a major role in engine health. 6. Can clog or stick. Sludge, carbon, or oil buildup can cause the valve to stick open or close. 7. Affects idle quality. A faulty PCV valve can cause rough idle, stalling, or vacuum leaks. 8. Connected to intake vacuum. The valve uses engine vacuum to control how much gas flows back into the intake. 9. Requires regular inspection. Many manufacturers recommend checking or replacing it every 40,000 to 80,000 kilometers, 25,000 to 50,000 miles. 10. Failure can damage the engine. A bad PCV valve can lead to oil contamination, sludge buildup, and increased engine wear. Main parts that make a car run: drivetrain and motion. 1. Engine creates power. The engine converts fuel into mechanical energy that moves the vehicle. 2. Transmission controls speed and torque. It adjusts engine power to match driving conditions, allowing the car to accelerate and cruise efficiently. 3. Clutch. Manual cars. The clutch connects and disconnects the engine from the transmission so gears can be changed smoothly. 4. Torque converter. Automatic cars. It transfers engine power to the transmission using fluid instead of a clutch. 5. Drive shaft transfers power. The drive shaft carries rotational power from the transmission to the differential, mainly in RWD and AWD vehicles. 6. Differential splits power. It allows the drive wheels to rotate at different speeds when turning, improving stability and control. 7. Axles deliver motion to wheels. Axles transmit power from the differential to the wheels so the vehicle can move. 8. CV joints allow flexibility. Constant velocity joints let axles bend and rotate smoothly as the suspension moves and wheels turn. 9. Wheels convert rotation into movement. Wheels receive torque from the drivetrain and move the car forward or backward. 10. Tires provide traction. Tires grip the road surface, allowing acceleration, braking, and steering to happen safely. Car engine. 1. The engine is the heart of the car. It generates the power needed to move the vehicle. 2. Converts fuel into motion. Engines turn fuel energy into mechanical energy through controlled combustion. 3. Most cars use internal combustion engines. These engines burn gasoline or diesel inside cylinders to produce power. 4. Cylinders determine engine size. Engine displacement depends on the number and size of cylinders. 5. Pistons move up and down. Pistons convert combustion pressure into mechanical motion. 6. Crankshaft turns linear motion into rotation. It transforms piston movement into rotational power. 7. Engines need air, fuel, and spark. Gasoline engines require air, fuel, and a spark to run. 8. Cooling systems prevent overheating. Radiators, coolant, and water pumps keep engine temperature controlled. 9. Lubrication reduces wear. Engine oil lubricates moving parts and prevents friction damage. 10. Modern engines are computer-controlled. The ECU monitors sensors and adjusts fuel, ignition, and timing for efficiency and performance. ECU, Engine Control Unit, the computer brain. 1. The ECU is the car's brain. It controls and manages the engine's operation electronically. 2. Monitors multiple sensors. It receives data from sensors like oxygen sensors, throttle position, coolant temperature, and airflow sensors. 3. Controls fuel injection. The ECU calculates how much fuel to inject into the engine for efficient combustion. 4. Manages ignition timing. It decides when spark plugs fire to optimize power and fuel economy. 5. Improves fuel efficiency. By constantly adjusting engine parameters, the ECU helps reduce fuel consumption. 6. Reduces emissions. The ECU works with systems like the EGR valve and catalytic converter to meet emissions standards. 7. Adapts to driving conditions. It adjusts engine behavior based on speed, load, temperature, and driving style. 8. Stores trouble codes. When something goes wrong, the ECU records fault codes that can be read with a diagnostic scanner. 9. Controls engine protection. It can limit engine power or enter limp mode to prevent damage when a serious issue is detected. 10. Can be reprogrammed or tuned. ECU tuning can increase performance, but improper tuning can reduce reliability and engine life. Throttle system. 1. Controls engine speed. The throttle system regulates how much air enters the engine, which directly affects engine RPM. 2. Works with the accelerator pedal. Pressing the gas pedal opens the throttle, allowing more air into the engine. 3. Airflow determines power. More air entering the engine allows more fuel to be burned, producing more power. 4. Older cars used cable throttles. Traditional throttle systems used a mechanical cable between the pedal and throttle body. 5. Modern cars use electronic throttle control, also called drive-by-wire. The throttle is controlled by sensors and the ECU. 6. Includes a throttle body. The throttle body contains a throttle plate, butterfly valve, that opens and closes to control airflow. 7. Uses throttle position sensors, TPS. These sensors tell the ECU the exact position of the throttle plate. 8. Helps control idle speed. The throttle system works with idle control systems to keep the engine running smoothly at idle. 9. Can affect drivability when faulty. Problems may cause hesitation, poor acceleration, or unstable idle. 10. Supports safety systems. Electronic throttles allow features like traction control, cruise control, and stability control to function. Transmission, manual or automatic. 1. Transfers engine power to the wheels. The transmission delivers engine power to the drivetrain so the car can move. 2. Controls speed and torque. By changing gear ratios, it balances engine power for acceleration, climbing, and cruising. 3. Manual transmissions use a clutch. The clutch allows the driver to engage or disengage the engine from the transmission when shifting gears. 4. Automatic transmissions shift on their own. They use hydraulic pressure, sensors, and computers to change gears automatically. 5. Torque converters replace clutches in automatics. A torque converter transfers power using transmission fluid instead of a mechanical clutch. 6. Modern automatics are computer-controlled. The transmission control module, TCM, decides shift timing based on speed, load, and throttle input. 7. Manual transmissions offer more driver control. Drivers choose when to shift gears, which can improve engagement and control. 8. Automatic transmissions improve driving comfort. They reduce driver effort, especially in traffic and city driving. 9. Transmission fluid is critical. It lubricates, cools, and helps transmit power. Low or dirty fluid can cause failure. 10. Failure affects vehicle movement. Transmission problems can cause slipping, hard shifting, delayed engagement, or complete loss of drive. Automatic transmission torque converter. 1. Replaces the clutch in automatic cars. The torque converter performs the same basic function as a clutch in manual transmissions. 2. Transfers engine power using fluid. It uses transmission fluid to send power from the engine to the transmission. 3. Allows the car to stop without stalling. The engine can keep running while the vehicle is stopped in gear. 4. Provides torque multiplication. At low speeds, it increases torque to help the vehicle accelerate smoothly. 5. Contains 3 main parts. The impeller, pump, turbine, and stator work together to transfer and multiply torque. 6. Works with engine RPM. Power transfer increases as engine speed rises. 7. Lock-up clutch improves efficiency. Many modern torque converters have a lock-up clutch to reduce slippage at cruising speeds. 8. Reduces drivetrain shock. Fluid coupling smooths power delivery and protects transmission components. 9. Uses transmission fluid for cooling. Proper fluid level and condition are critical for torque converter operation. 10. Failure causes drivability issues. A bad torque converter can cause shuddering, slipping, overheating, or poor acceleration. Manual transmission clutch. 1. Connects and disconnects engine power. The clutch allows power to flow from the engine to the transmission when engaged. 2. Enables smooth gear changes. Pressing the clutch pedal lets the driver shift gears without damaging the transmission. 3. Uses friction to transfer power. The clutch disc grips the flywheel through friction when engaged. 4. Consists of key components. Main parts include the clutch disc, pressure plate, flywheel, and release, throwout, bearing. 5. Operated by the clutch pedal. The pedal controls engagement through a cable or hydraulic system. 6. Wears over time. Normal use causes the clutch disc to wear and eventually require replacement. 7. Slipping reduces performance. A slipping clutch causes engine RPM to rise without increasing vehicle speed. 8. Helps prevent drivetrain damage. It absorbs shock during engagement, protecting gears and axles. 9. Improper use shortens life. Riding the clutch or aggressive launches increase wear. 10. Failure affects drivability. A bad clutch can cause hard shifting, shuddering, burning smells, or inability to move the car. Flywheel. 1. Stores rotational energy. The flywheel helps maintain smooth engine rotation between power strokes. 2. Mounted on the crankshaft. It is bolted directly to the rear of the engine's crankshaft. 3. Works with the clutch. In manual cars, the clutch presses against the flywheel to transfer engine power. 4. Helps start the engine. The starter motor engages the flywheel's ring gear to crank the engine. 5. Reduces engine vibration. Its mass smooths out engine pulses and reduces vibration. 6. Made from heavy materials, usually constructed from cast iron or steel for strength and durability. 7. Dual mass flywheels exist. Many modern cars use dual mass flywheels to reduce drivetrain noise and vibration. 8. Wears over time. Heat and friction can cause surface wear, hot spots, or cracking. 9. Affects drivability. A damaged flywheel can cause clutch chatter, vibration, or slipping. 10. Weight affects performance. Lighter flywheels improve throttle response. Heavier ones provide smoother operation. Car gearbox. 1. Transfers engine power. The gearbox sends engine power to the drivetrain and ultimately to the wheels. 2. Changes gear ratios. Different gears allow the engine to operate efficiently at low speeds, high speeds, and under heavy load. 3. Works with the transmission system. The gearbox is the core mechanical unit inside the transmission. 4. Manual and automatic versions exist. Manual gearboxes use driver-controlled gears, while automatic gearboxes shift gears automatically. 5. Improves acceleration and cruising. Lower gears provide more torque for acceleration. Higher gears reduce engine RPM for fuel efficiency. 6. Contains multiple gears and shafts. Gears, bearings, synchronizers, and shafts work together to manage power flow. 7. Requires lubrication. Gear oil or transmission fluid reduces friction, wear, and heat inside the gearbox. 8. Synchronizers enable smooth shifts. In manual gearboxes, synchronizers match gear speeds to prevent grinding. 9. Wear causes shifting problems. Worn gears or synchronizers can cause hard shifting, grinding, or gear slipping. 10. Essential for vehicle movement. Without a functioning gearbox, the engine's power cannot be properly used to move the car.